The next section deals with the reduction of benzene. So reducing a benzene molecule. If you remember from Organic Chemistry 1 and probably from this class as well, one of the simplest ways to view reduction in organic chemistry is to view it as adding hydrogen, or losing oxygen. Well, since there's no oxygen in benzene, it must mean that we're gaining hydrogen. So if you were to hydrogenate benzene, which can only be done under very forceful conditions to produce cyclohexane, that would be considered a reduction, right? We're adding hydrogens. You can see that you end up losing 208 kilojoules per mole. However, an alkene can be selectively hydrogenated in the presence of a benzene ring. Why can that be done? Because you notice here that it takes 100 atmospheres, right? That's 100 times atmospheric pressure in order to do this reaction. That's very forceful conditions. So if we just take the same, aromatic ring, and we just have this double bond over here, right? This is called styrene. So if we take styrene, okay, and we just mildly hydrogenate that at 2 atmospheres. So that's only 2 times atmospheric pressure, really low temperature, only 25 degrees Celsius as opposed to cranking it up. Well, we can just hydrogenate that double bond that's outside of the ring. That's a very useful reaction. So much milder conditions for the hydrogenation of that group outside of the ring. And that's not reducing the benzene ring, but that's a hydrogenation of that double bond. Well, we can also reduce benzene via a reaction that's named after a chemist. It's called the Birch Reduction. Birch is not after the tree, it's a person's name. If we take an aromatic ring, benzene ring, and we treat it with sodium and methanol with ammonia, we can reduce it to make this molecule here. So we've lost one of the double bonds, right? We added a total of 2 hydrogens, right? We added one here and we added one here. Right? Somehow. Where did those hydrogens come from? Well, we're going to take a look at the mechanism in just a second. But this is not outside of the realms of possibility, because you remember that when we looked at the dissolving metal reduction of an alkyne, we took that alkyne, we treated it with sodium in liquid ammonia, and we added hydrogens that way too, didn't we? Right? We ended up adding 2 hydrogens overall in the reaction. So let's take a look at the mechanism of this Birch reduction. Well, you know that sodium is a group 1A in the periodic table. If you look at sodium, it's element number 11. Again, it's in group 1A. That means it's got 1 valence electron. All right, if I was to ask you to draw me the Lewis structure of sodium, you would just say sodium with a dot. So we have sodium, and we know that sodium has a low ionization energy. It's ready to lose an electron, because if it loses 1 electron, it becomes isoelectronic with neon. So if the sodium loses an electron, we end up donating that electron to the aromatic ring, and we form what's called a radical anion. Why is it a radical anion? Because it's got a radical in it and an anion in it. Now, if you've got that radical anion, that anion can rip a proton off of a methanol molecule. So now you've added 1 hydrogen to the aromatic ring. Now you've got a radical. You can probably guess what's going to happen next. It's going to react with another element of sodium. Right? It's going to donate another electron. When it donates another electron, we create now just a plain old anion, and that anion is going to rip a proton off of methanol. And so we're going to end up with the 1,4-cyclopentadiene molecule, right? This is 1,4-cyclohexa, jeepers, cyclohexadiene. There we go. So the reason that they color-coded these hydrogens, right, they highlighted them in red, is so that you knew they came from the methanol molecule. So that's where the protons come from in the Birch reduction. Now, what's interesting about the Birch reduction is that there's some regioselectivity that you've got to take into account depending on the substitution of an aromatic ring. Right, the Birch reduction, it doesn't completely reduce the ring, okay? The product has 2 sp3 hybridized carbons that are on opposite ends of the ring. Now, again, getting back into that regioselectivity thing here, depending on whether you have an electron donating alkyl group, okay, or an electron donating group, okay, versus, and that's what this whole next section is about, electron donating groups versus electron withdrawing groups. That's going to determine where the double bonds are. So let's say you have an alkyl group, right? You know that alkyl groups are electron donating, right? Alkyl side groups are going to be electron donating via hyperconjugation. I think I'm getting tired. Hyperconjugation. Okay. So if you have an electron donating group, right, something that's donating electron density, it's not going to be reduced at that position, the position where the electron donating group is. Why? Because it's going to destabilize the radical cation that's formed. Right? Think about it. If you had an electron donating group, let's just draw the radical cation. So we'll put the two double bonds, put the anion here, we'll put the radical here. Well, if I have an electron donating group here, an alkyl group, electron donating group, right? This is going to be highly disfavored because now I'm donating electron density towards something that's already negative. And so that's why the electron is not going to be donated onto this carbon. It's going to be donated on one of the carbons next door, okay? So that you end up with a double bond attached to the carbon where the electron donating group is. However, if you have an electron withdrawing group, then it's the opposite that occurs, right? The radical anion that would be formed in this case, intermediate, would look like this. You have something like this. You put your anion here, your radical here, but now you've got an electron withdrawing group, okay? So since this is sucking electron density away, right, a carbonyl is electron withdrawing, it's going to stabilize that radical anion. And that's why the regioselectivity, when we have an electron withdrawing group, EWG, is such that the carbon that's attached directly to it does get reduced. With all that in mind, let's take a look at some problems where we have to do some syntheses.